Voyager is not just drifting in deep space, it's currently skimming the real edge of the solar system in a region no human instrument had ever reached before. Out there, the sun's influence is fading, the galaxy is starting to take over, and the readings coming back are so strange they force scientists to redraw the boundary of our home system from scratch. In this video, you're going to follow Voyager right up to that frontier and see what space really looks like when you step outside the sun's protection. But before we continue, please subscribe to the channel to give your support. Let's continue. Out there, Voyager is more than 170 astronomical units from the sun. That's over 25 billion kilometers, 16 billion miles. At that distance, sunlight has dropped by a factor of around 25,000 compared to what you get on Earth. You would have permanent night with a hard point of light where the sun is, and when Mission Control sends a radio signal, it needs almost 22 hours just to get there, then another 22 hours for any reply to come back. Every instruction is a full-day question and answer cycle with a spacecraft that is old and running on tiny amounts of power. That delay means you can't joystick a probe like that. You send a command, you wait, you look at a few bits of data, you wait again. So when we say we are flying Voyager, what we really mean is that engineers predict what will happen, program it in advance, and then trust that the spacecraft will do it on its own. And all of this is happening at a distance where the orbit of Neptune, around 30 astronomical units, is far behind. Most of the planets are squeezed into a small inner zone compared to where Voyager is now. The natural follow-up is speed. If it is that far, maybe it is also moving at a big fraction of light speed. That sounds like what you would need to cross interstellar space, but the numbers tell a different story. Voyager is fast by normal engineering standards. It is traveling at about 17 kilometers every second. That's around 61,000 kilometers per hour, about 38,000 miles per hour, faster than a rifle bullet, faster than any crewed vehicle ever built. If you compare it to a racehorse, you're looking at more than 20 times a top race speed, and it has kept that up for decades without refueling. Still, set that next to the scale of the galaxy and it looks slow. At that speed, crossing just 1 light year would take close to 18,000 years. The nearest star system is more than 4 light years away. So the message is simple. We have sent something far, and it is nowhere near the stars. When people talk about going to another star, they skip the step where you realize that even our fastest probes barely make a dent in the distance, which is why defining the true border of the solar system matters. For many years, the answer you would get in a classroom would be the solar system ends at Pluto, or maybe at the Kuiper Belt, that icy ring beyond Neptune full of dwarf planets and smaller bodies. That feels clean. You list the major objects, you put a line just beyond them. But that is not how space works. Gravity from the sun extends much farther, and the sun is not only pulling on things, it is also pushing material out in the form of the solar wind, that constant flow of charged particles and magnetic field that streams outward in all directions. This wind carves out a cavity in the thin gas between the stars, the interstellar medium, and that cavity is what you actually live inside. We call it the heliosphere, a bubble of solar wind and magnetic field around the sun. Inside it, the behavior of plasma, radiation, and magnetic fields is dominated by the sun. Outside it, those same things are controlled by the gas and fields that belong to the galaxy itself, to the very local interstellar medium around our system. So your real physical border is not a ring of rocks, it's the place where the solar wind stops being stronger than the outside environment. That outer surface is called the heliopause. It's the contact region between the solar wind and the interstellar medium, and this is where Voyager becomes crucial. Voyager 1 crossed at about 121 astronomical units. Voyager 2 crossed at about 119, but in a different direction and at a different latitude above the solar equator. If the heliosphere were a perfect sphere, smooth and centered, you would expect them to cross at almost the same distance. Instead, the numbers are different, so we know the bubble is not symmetric. It's squashed and distorted, probably by the direction the sun is moving through the galaxy and by the local interstellar magnetic field pressing on it harder from some directions than others. On top of that, the outer surface is not a solid surface. It's more like a moving, irregular transition layer than a clean shell. As Voyager moved outward, it didn't see one neat jump and then complete stability. It saw changes in particle densities, changes in magnetic field strength, changes in the types of particles it was detecting. When people used to draw the edge of the solar system as a tidy line, that was basically a guess. Voyager showed that the real border is a dynamic shock front shaped by both the sun and the galaxy. Now, why should you care about any of this if you're sitting on Earth at 1 astronomical unit? All of this sounds far away. But it's not just geometry. That bubble around the sun acts as a shield. The heliosphere reduces the number and energy of galactic cosmic rays that reach the inner system. Those are high-energy particles that come from supernova events and other violent events in the galaxy. Inside the bubble, the solar wind and the sun's magnetic field deflect a significant fraction of them. Outside the bubble, that protection drops, and the raw cosmic ray environment is harsher. Voyager, by sampling the conditions near and beyond the heliopause, gives you numbers for that change, how much the radiation level rises, how the particle densities differ, how the magnetic fields behave. Those measurements tell you how special our shielded zone around the sun is, and how fragile it might be. They also set the baseline for any future mission that wants to go beyond the heliosphere with people or more advanced probes. In other words, to understand what it really means to leave the solar system, you need the kind of data Voyager is sending back from more than 170 astronomical units away. So the next step is, before you even get to that outer boundary, what happens to the solar wind on the way out? Where does it slow down, heat up, and begin to lose the fight against the galaxy's push? And what did Voyager actually see when the sun's wind started to run out of breath? Here's a simple question. If the sun is blowing a wind in all directions, how far can that wind actually run before it starts to fail against the galaxy around it? Close to the sun, space is full of charged particles streaming outwards. This is the solar wind. Right near Earth's orbit, that wind is moving at a few hundred kilometers per second. Around 400 kilometers per second is a typical fast value. That's over 1,000,000 kilometers per hour, more than 600,000 miles per hour, several times faster than a rifle bullet. It's not a gentle breeze. It's a constant outflow of plasma, electrons, and protons carrying the sun's magnetic field with it. As this wind moves out, it spreads over a bigger and bigger sphere, so its density drops. The farther you go, the fewer particles you get in each cubic centimeter of space. But the speed stays high while the wind is still supersonic. In plasma physics, that means it's moving faster than the local speed of sound in the plasma. And as long as that's true, the flow doesn't really care about what's ahead of it. It barrels through. Then, way out beyond the planets, it starts to feel the pressure of the interstellar medium pushing back. Like any flow that runs into resistance, at some point it has to slow down. It cannot stay supersonic forever. And when a supersonic flow slows down fast, you get a shock, a sharp boundary where conditions change suddenly. So the big unknown for decades was very clear. At what distance from the sun does the solar wind finally hit that shock? When does it go from supersonic to subsonic and admit it's losing ground? That first major boundary is called the termination shock, and this is where Voyager earned its place in every serious discussion about the edge of the solar system. Voyager 1 reached that shock at about 94 astronomical units from the sun. Voyager 2 crossed it closer in at around 84 astronomical units. Both spacecraft are going outward, but in different directions and slightly different latitudes. And that difference in distance is the first big clue that our heliosphere is not shaped like a perfect sphere. If the bubble carved by the solar wind were smooth and symmetric, you'd expect both spacecraft to hit the termination shock at roughly the same radius. Maybe a small difference, but not 10 astronomical units. Instead, Voyager 2 met the shock earlier, which tells you the heliosphere is squashed and distorted. The sun is moving through the local interstellar medium, and the external magnetic field and gas pressure are pushing harder from some directions than others. The shock is closer in on the upwind side, and farther out on others. At the termination shock itself, the solar wind drops in speed, heats up, and becomes more turbulent. The flow goes from supersonic to subsonic, which means information and waves can now move upstream, back toward the sun. The plasma there is more chaotic, more compressed, and hotter. If the heliosphere were a human body, this is where the sun's breath starts to wheeze. Not a clean and powerful outflow anymore, but a slowed, heated, stressed flow that knows it's pushing against something tougher. So what does that actually look like in numbers? How empty is the space out there, and how much does it change when you cross this boundary? In the outer heliosphere, just inside the termination shock, the plasma density is around a couple of thousandths of an electron per cubic centimeter, about 0.002 electrons in that volume. That is an incredible vacuum. High-end vacuum chambers on Earth, built specifically to be almost empty, or still denser than that. They have more particles rattling around than the space environment Voyager is cruising through, and that's already in the inner region, still under the sun's control. When Voyager crossed the termination shock, its instruments saw the solar wind speed drop, the density rise, and the temperature climb. The flow converted some of its bulk motion, that straight-line speed, into heat and random motions. The result is a region called the heliosheath. This is the layer between the termination shock and the heliopause, a messy transition zone where the slowed solar wind and the interstellar medium are starting to interact more directly. Inside the heliosheath, the plasma is hotter than it was just inside the shock, but it's also slower and more turbulent. There are regions where the outward flow nearly stalls, patches where the sun's wind is basically piling up. This is not a clean, thin shell. It's a whole volume of stressed, compressed plasma, and it's the last piece of territory that still belongs to the sun before you get to the true border with interstellar space. Before Voyager actually flew through this region and took data, most models treated the termination shock as a simple spherical layer. You'd see it drawn as a smooth contour around the sun. One radius, one jump, very tidy. Those models were based on best guesses about the solar wind and interstellar medium, plus fairly simple assumptions about symmetry. It looked good on paper, but it was a guess. Voyager's data tore that picture apart. As the spacecraft approached and crossed the shock, they did not just see one clean jump from one regime to another. They saw ripples. They saw variations in time. They saw evidence that the shock itself moves in and out as the sun's activity changes. They saw zones in the heliosheath where the outward solar wind speed was almost zero, stagnation regions where the sun's wind had piled up and lost its forward drive. Those features tell you the outer heliosphere is dynamic and structured, not a solid static shell, but a churning volume of stressed, compressed plasma, and it's the last piece of territory that still belongs to the sun before you get to the true border with interstellar space. So how do you know the exact moment the sun really lets you go? When you stop living in solar space and start living in galactic space. By the time Voyager 1 was in the outer heliosphere, it had already passed the termination shock and was moving through that slowed, heated, messy solar wind. Then, on August 25, 2012, when it was about 121 astronomical units from the sun, roughly 18 billion kilometers, around 11 billion miles, the data changed in a way nobody had ever seen before. Charged particles from the sun dropped off hard. Galactic cosmic rays jumped up. The magnetic field strength increased. It looked exactly like what models said the edge of the heliosphere should look like. But there was a problem. The one instrument that directly measures plasma speed and density on Voyager 1 had failed years earlier, so the team could see particle counts and magnetic fields, but not the basic how many electrons per cubic centimeter is out there number. And without that, some scientists argued that maybe Voyager was still in a weird outer layer of solar wind, some kind of heliosheath plus region. So even after August 2012, there was real debate. Had humanity actually stepped into interstellar space or just into a stranger part of our own bubble? The key question became very sharp. If you can't taste the plasma directly, how do you prove you're not stuck in the last fumes of the sun's wind? Before the crossings, theory was pretty clear on one thing. If you move from the outer heliosphere into the very local interstellar medium, the plasma density should jump a lot. Just inside the heliopause, you expect around a couple of thousands of an electron per cubic centimeter, about 0.002 electrons in that volume. That is an incredible vacuum. High-end vacuum chambers on Earth, built specifically to be almost empty, are still denser than that. They have more particles rattling around than the space environment Voyager is cruising through, and that's already in the inner region, still under the sun's control. When Voyager crossed the heliopause, the team could see the plasma density jump, up to values similar to what Voyager 1 had inferred with plasma waves, again in that range of a few hundredths of a particle per cubic centimeter, about 0.08, right in the middle of the expected interstellar range, nowhere near the low values inside the heliosphere. And later events gave similar results. Each time a shock from the sun passed by and excited the plasma, you got another reading, and the numbers stayed in that interstellar band. That was the smoking gun. If the plasma were still under the sun's control, the density would not sit in that higher range. It matched the models for the local interstellar medium, not the outer solar wind. From that point on, the argument was basically done. By the time you're listening to this, Voyager 1 has been flying in interstellar plasma for years, still strongly feeling the sun's gravity, but no longer embedded in the sun's own wind. You might still ask though, what if this was some freak path? What if Voyager 1 happened to cross at a strange spot, and the heliopause is thicker or weaker, or shaped differently elsewhere? How do you know this isn't just a one-off, a weird edge case? That's where Voyager 2 becomes crucial. Unlike Voyager 1, Voyager 2's plasma instrument is still working. It can directly measure the density and speed of the particles around it. On November 5, 2018, when it was about 119 astronomical units out, a little closer than Voyager 1's crossing distance and in a different direction, its instrument saw a sharp change. The outflowing solar wind speed dropped to nearly zero. Then, outside the boundary, the plasma density jumped up to values similar to what Voyager 1 had inferred with plasma waves, again in that range of a few hundredths of a particle per cubic centimeter. This is nowhere near the low values inside the heliosphere. Because Voyager 2 had working plasma detectors, the team could also estimate how thick the heliopause was along its path. The transition from solar wind plasma to interstellar plasma happened over a distance of less than a tenth of an astronomical unit, under 15 million kilometers, about 9 million miles. On the scale of the solar system, that is razor thin. It's like having a whole planetary system and then a boundary layer that, compared to that system, is almost a sheet. Just inside that thin layer, Voyager 2 saw the plasma slowing and compressing. The solar wind was being squeezed as it hit the heliopause, as if the interstellar medium outside was pushing inward, raising the pressure. This is a direct hint about the balance of forces. The sun's outflow is strong, but the external gas and magnetic field are not weak. They are capable of crushing and reshaping the outermost parts of your heliosphere. You could think, with a boundary that thin and a density jump that sharp, maybe the heliopause is a clean, simple surface. Cross once, everything changes, then it's quiet and uniform on the other side. One step and you're in calm, steady interstellar space. That would be comforting. It would also be wrong. Voyager's instruments show that even beyond the heliopause, the environment is not static. The plasma density keeps changing, the magnetic field strength fluctuates, and those changes can be tied back to events at the sun. A massive eruption on the solar surface, a coronal mass ejection, can drive a shock wave that travels outward for years, eventually hitting the heliopause, disturbing it, then transmitting part of that disturbance into the interstellar medium. So the heliopause moves, flexes, and shifts. It is not a fixed border drawn once in space. It responds both to solar activity and to variations in the local interstellar medium. This means that when you say Voyager is in interstellar space, you are not talking about a quiet, empty void. The data show a busy borderland with waves, shocks, and turbulence. The sun is still sending out pulses that reach all the way to this frontier, and the galaxy is still pushing back, changing the shape and position of the boundary. Voyager is not just drifting in a calm darkness, it is sitting in the middle of a constantly negotiated truce between a star and its surroundings. And this sets up the next key question. If the plasma and magnetic field change so sharply at this living boundary, what happens to the high-energy radiation from the galaxy itself? How does the flow of cosmic rays transform when you move from inside the sun shield to the raw environment outside? How do you know the sun is actually protecting you, not just lighting you? How do you prove that this bubble you live in is blocking something genuinely dangerous from the rest of the galaxy? Deep inside the heliosphere, the magnetic field carried by the solar wind bends and scatters a lot of the most energetic charged particles that come in from outside. These are galactic cosmic rays, high-energy protons and heavier nuclei launched by supernova explosions and other violent events in the Milky Way. They travel near the speed of light, and they are very good at damaging DNA and electronics. When they try to enter the heliosphere, they do not just fly straight in. They feel the tangled magnetic fields of the solar wind, but get deflected, slowed, sometimes trapped and redirected. The result is simple. The intensity of galactic cosmic rays inside the bubble is significantly lower than it would be in raw interstellar space. That reduction is part of why life can exist on a planet like Earth, sitting at about 1 astronomical unit, under an atmosphere with a pressure of about 1 bar. You already deal with cosmic rays. They create particle showers in the atmosphere and contribute to background radiation, but they are moderated. The combination of the heliosphere, Earth's magnetic field, and the atmosphere takes the edge off. Without that heliospheric shield, the spectrum and intensity of incoming particles would be harsher, and everything from cancer risk to mutation rates and material aging would look different. So, if the heliosphere is really acting like a shield, you should see that shield fail as you move toward the boundary. You should see the galaxy's radiation get stronger, not in theory, but right there in the detector readings. As Voyager 1 moved past about 110 astronomical units and then toward roughly 120 astronomical units, its radiation detectors started to record something no spacecraft had seen before. The flux of high-energy galactic cosmic rays climbed, not by a tiny fraction, but by tens of percent over just a few astronomical units of travel. That is a big change over a relatively small radial distance. At the same time, the intensity of lower energy particles that originate inside the heliosphere, particles accelerated by the sun and its shocks, dropped sharply. Those two trends together are very clear. Fewer homegrown particles, more galactic particles. That is exactly what you expect if you're moving from the sun's radiation environment into the galaxy's environment. This behavior was not a one-step jump. Just inside the heliopause, the change was steep. As Voyager 1 crept outward, the intensity of galactic cosmic rays increased with a gradient on the order of 20% per astronomical unit. That is a very strong radial gradient. It means each extra unit of distance near the boundary adds a significant dose of radiation. Then, once Voyager was fully outside, in interstellar plasma, the curve flattened. The intensity of galactic cosmic rays stopped rising as fast and settled into a more stable level. That tells you the main modulation is happening inside or just at the heliopause. Once you are truly in interstellar space, the background becomes more uniform. In plain terms, that's like walking across a zone where your radiation exposure jumps hard over a distance smaller than the diameter of Earth's orbit. If you think about future crewed missions that ever get close to this region, that gradient matters. If your spacecraft crosses from deep inside the bubble to just outside, your shielding design and mission planning have to assume that dose rates could rise quickly over a relatively short distance. You cannot treat interstellar radiation as something that increases gently and slowly. The data say there's a sharp ramp near the edge, and then a new higher baseline outside. Numbers like 20% per astronomical unit may sound abstract, but they feed directly into risk calculations. How long can a crew safely stay in a given region? How much mass do you need in shielding material? How often will electronics suffer bit flips or permanent damage? Before Voyager, these estimates were based on indirect evidence and models. Now there are real measurements showing how intense the transition can be. Before these crossings, many cosmic ray modulation models treated the heliopause as a kind of semi-permeable barrier, a membrane where cosmic rays slowly diffuse in, get scattered, and gradually leak into the heliospheric. That picture implied a smoother curve in intensity as you move outward, a smooth roll-off rather than a sharp step. The Voyager data don't match that simple view. Instead of a gentle roll-off, you see a structured, steep transition, more like going from one regime to another over a narrow zone, with strong gradients and clear signatures. That means the interaction between cosmic rays and the heliospheric magnetic field is more complex than those older models assumed. The turbulence in the solar wind, the geometry of the magnetic field lines, and the structure of the heliopause itself all affect how particles get in and out. The sun appears to provide stronger shielding at certain energies and directions than expected, and less in others. So the heliosphere is not a uniform passive filter. It's an active, structured barrier whose properties you now have to tune to match actual measurements. For planetary atmospheres, especially for any world without a strong magnetic field of its own, this matters a lot. If the heliosphere's shield is sharper and more effective at its boundary, then changes in solar activity and in the local interstellar environment can have a more direct impact on the radiation that reaches those worlds. When you apply this to exoplanet systems, the lesson is clear. You cannot talk about habitability without also talking about the shape and strength of that star's astrosphere and how it modulates cosmic rays. So, you now know that the particle environment changes violently at the edge. But there is another piece of the puzzle that turned out to be just as surprising. If you expect a clean flip in the direction of the magnetic field when you cross into interstellar space, what do you do when the data show that the field outside refuses to turn the way you thought it would? If the sun's bubble really ends at the heliopause, shouldn't the magnetic field outside point in a clearly different direction? How else do you prove you've switched from the sun space to the galaxy space? Inside the heliosphere, the magnetic field is basically the sun's field stretched, then wound up by rotation and solar wind. It forms what's called a spiral pattern, because as the sun spins and the wind flows outward, the field lines get dragged into curved shapes. By the time you're out near Jupiter or Saturn, that spiral is clear in the data. You see a consistent pattern in direction. You are following the sun's magnetic geometry. Outside the heliosphere, you expect something else. The Milky Way has its own large-scale magnetic field, and the local interstellar medium around us has a field direction you can estimate from other observations. So the prediction before Voyager crossed the heliopause was straightforward. Inside, you follow the sun's spiral. Outside, you align with the galaxy's field. Cross the boundary, and the magnetic direction should swing by something like tens of degrees, maybe close to a right angle. In other words, the magnetometer on Voyager should show a clear, dramatic flip. Teams were literally watching the field direction readouts waiting for that big rotation. A sharp change would have been the clean, simple signature that you'd left the sun's field and entered the galactic field. But when Voyager 1 actually crossed, that is not what happened. The magnitude of the field went up, which fit the idea of a compressed region at the boundary, but the direction only rotated modestly. It did not snap into a new orientation that was clearly incompatible with the inner heliosphere pattern. So you get a strange result. The density says you are outside, the cosmic ray profile says you are outside, the plasma wave frequencies say you are outside, but the magnetic field direction still looks surprisingly similar to what you had just inside. Not identical, but not the big, obvious flip that many people expected. This is why there was so much debate for years after 2012. People asked, how can you be in interstellar space if the field direction hasn't dramatically changed? There are two broad ways to explain this, both of them uncomfortable for earlier simple models. One option is that the sun's magnetic field lines drape around the heliopause and twist in a more complicated way than we thought. So even outside the main flow of the solar wind, the local field direction is still influenced by the geometry of the sun's field. It's like the field lines are being bent and wrapped along the boundary, carrying some of their old orientation with them into the very first parts of interstellar space near the heliopause. The other option is that the local interstellar field, by coincidence or due to the history of this region of the galaxy, happens to be aligned not too far from the direction of the heliospheric field just inside the boundary. In that case, you could cross into the galaxy's field and not see a huge turn because the two directions are already not that far apart. Neither explanation is fully satisfying, and both force you to drop the simple picture where you go from a clearly solar field to a clearly galactic one with a big jump in direction. Then there's the question of strength, not just direction. Before Voyager crossed, a lot of models assumed the interstellar field just outside the heliopause would be relatively weak. Many estimates were below half a nanotesla. A nanotesla is a tiny unit. Earth's surface field is around 50,000 nanoteslas. So you're talking about a field roughly 100,000 times weaker than the one your compass uses. But on scales of tens of astronomical units, even that small field is dynamically important. Voyager's magnetometer measured values in the range of about 0.4 to 0.5 nanoteslas just outside the heliopause, which is higher than many of those earlier predictions. That might sound like a minor correction, but it has big consequences. If the interstellar field is stronger than expected, it can push harder on the heliosphere, it can squash it more, and it can control how the boundary layers are shaped and how stable they are. Think about the balance here. On one side, you have the pressure of the solar wind and its embedded magnetic field. On the other side, you have the pressure of the interstellar gas and magnetic field. If the external magnetic part is stronger, it doesn't take much material density to significantly influence the shape of the bubble. The heliosphere becomes less like a free expanding cloud and more like something being compressed and pinched by the outside environment, especially in directions where the external magnetic field lines connect efficiently to the heliopause. This fits with what you saw earlier from the different crossing distances. Voyager 1 hits the termination shock at about 94 astronomical units, and the heliopause at about 119. Voyager 2 hits the termination shock at around 84 astronomical units, and the heliopause at about 119. Those numbers alone tell you the bubble is asymmetric. Now add a stronger, misaligned external magnetic field, and you can start to see why the shape would not be a simple sphere or a long, smooth comet tail. Recent models that include these Voyager constraints, the higher external density, the unexpectedly strong field, and the odd field directions, tend to favor a more complex geometry. Instead of a neat teardrop, you get something more like a double-lobed structure, sometimes described as a croissant-shaped, with two broad lobes and a more compact, disturbed region trailing downstream. That shape comes from the way the interstellar magnetic field channels plasma flows and directs how the solar wind can escape on the downwind side. Voyager does not give you a full three-dimensional map. It's just two probes cutting through two specific paths, but those paths are enough to anchor the simulations. You know at which distances the key boundaries appear along those lines, and you know what the field strength and direction look like there. That means any serious model of the heliosphere now has to reproduce those numbers. You cannot just draw a nice comet tail and call it done. You have to show how a stronger, structured external magnetic field can sculpt the sun's bubble into something that matches the data. This is not just a matter of pretty diagrams. The shape of the heliosphere affects where cosmic rays can leak in more easily, how solar material escapes into the galaxy, and how future interstellar probes should plan their trajectories to minimize radiation exposure or take advantage of certain regions. If the field outside is stronger and differently oriented than you thought, then the safe and unsafe routes through the boundary will not match older expectations. So now you have a picture where the magnetic field direction outside refuses to give you a simple flip, and the field strength outside is strong enough to reshape the entire bubble. The obvious next question is, in this environment, what is the actual state of the interstellar plasma around you? How dense is it? How hot is it? And how did Voyager manage to measure any of that in such an extreme vacuum? How do you measure what space is made of when there are so few particles that a normal detector basically sees nothing but silence? Out where Voyager 1 is now, the plasma is so thin that counting individual electrons directly is almost impossible. The particle instruments can give you some information, but the numbers are tiny, so you use a different trick. You listen how the plasma rings. In a charged gas, electrons can oscillate together at a natural frequency, a bit like a group vibration. If something disturbs the plasma, a shock or a burst of energy from the sun, those electrons start to oscillate. That creates electric field fluctuations you can pick up as radio tones. Voyager's plasma wave instrument is built exactly for that. It doesn't see individual particles. It measures tiny electric fields at audio-like frequencies, and you can convert those frequencies into a density because the oscillation rate depends directly on how many electrons sit in each cubic centimeter. Higher density, higher frequency. Lower density, lower frequency. So, when Voyager hears tones in the range of a couple of thousand cycles per second, around 2 to 3 kilohertz, that maps to electron densities of a few hundredths of per cubic centimeter, roughly between 0.05 and 0.08. Those are the values you expect in the very local interstellar medium, not inside the heliosphere. This is why those interstellar conformation events matter so much. A solar blast travels outward, hits the plasma near Voyager, shakes it, the electrons ring, the instrument hears a specific pitch, and from that pitch you can say, out here, this far from the sun, the number of electrons per cubic centimeter is in the interstellar range. It's a very indirect method, but it's one of the only ways to get density in a place where you might have just a few tens of thousands of particles in a cubic meter. Once you can measure density like this, the next question is, how big is the jump when you leave the heliosphere? How different is the outside from the inside? Inside the outer heliosphere, just before the heliopause, the plasma density is around a couple of thousandths of an electron per cubic centimeter, about 0.002. That is already a ridiculously good vacuum, better than most ultra-high vacuum systems on Earth. Then you step outside, and Voyager's plasma wave measurements show values around 0.08 per cubic centimeter, sometimes a bit lower, sometimes a bit higher. That is an increase by a factor of around 40 to 50. You are still dealing with an extreme vacuum. There are far fewer particles out there than in air, or even in the best lab vacuum you can build. But for the physics that controls shocks, waves, and how particles are accelerated, that density jump is huge. A higher density plasma carries more current, reacts differently to magnetic disturbances, and lets different kinds of waves propagate. So the interstellar medium just outside the heliosphere is not just a bit thicker, it is a fundamentally different regime with its own characteristic behavior. That big jump is one of the reasons we say the heliopause is a real physical boundary, not just a vague region. You go from a very dilute solar wind to a significantly denser galactic plasma over a relatively thin layer. And once you are outside, you're no longer in a space controlled by the sun's outflow. You're in material that belongs to the galaxy. Density is only half the story, though. The other half is temperature, and this is where the numbers sound misleading if you try to map them directly to everyday experience. How do you process the idea that the gas around Voyager is both cold and thin, and also tens of thousands of degrees at the same time? Voyager 2, unlike Voyager 1, still has a working plasma instrument that can measure particle speeds more directly. From those speeds, you can infer a temperature. The velocities indicate that the interstellar plasma just outside the heliopause sits in a range of roughly 30,000 to 50,000 Kelvin. That is tens of thousands of degrees above absolute zero. On paper, that sounds incredibly hot, hotter than many surfaces on Earth. But this is not a temperature you would feel the way you feel air temperature on your skin. Temperature in a gas is about the average kinetic energy, the average speed of the particles. In the interstellar medium, each particle has a lot of energy, but there are very few particles per cubic meter, so the energy per particle is high, but the energy per volume is tiny. If you put a solid object there, very few particles would hit it each second, so it would not warm up quickly. You'd be in a medium where each individual proton is red hot in energy terms, but the overall environment is so empty that it cannot transfer heat efficiently. This is why calling that plasma hot can be confusing. In physics terms, yes, the temperature is high. In human terms, your spacecraft is not being baked. It is being tapped occasionally by fast particles in an almost empty volume. It's a regime that barely maps to everyday experience, because you never deal with both such low density and such high particle energies on Earth without specialized equipment. Once Voyager's outside, measuring both density and effective temperature, you can start asking a larger scale question. Does the environment out there stay constant, or does it keep changing as you move farther from the sun? Is the very local interstellar medium smooth, or does it have structure on the scale of tens of astronomical units? Analyses of several years of plasma wave data from Voyager 1 show that the electron density does not stay flat once you cross the heliopause. Instead, as the spacecraft moves another several tens of astronomical units outward, the inferred density gradually increases, not in a sharp jump this time, but in a slow upward trend. You can see the shift in the frequencies of those plasma tones. They creep higher over time, which means more electrons per cubic centimeter, even though you are far beyond the sun's main influence. That gradual rise hints at larger scale structure in the very local interstellar medium. You're not traveling through a perfectly uniform gas. You're moving through regions with slightly different densities, maybe shaped by past supernova shocks, local magnetic field patterns, or flows of gas relative to the sun's motion. It suggests that the environment our heliosphere is plowing through is made of subtle filaments, waves, and patches of varying density, rather than one smooth background. For models of the heliosphere, that matters. If the external density is not constant, then the pressure on the heliopause is not constant either. Regions of higher density can squeeze the bubble more. Regions of lower density can let it expand slightly. Over long timescales, that could change the size and shape of the heliosphere in ways we are only beginning to quantify. And it means the sun is moving through a textured medium, not an ideal gas. All of that sets up an even more dynamic picture. You have a boundary where density jumps sharply, you have a background plasma outside that slowly varies, and you have a sun that keeps throwing out shocks and eruptions. The obvious next question is, when those old explosions from the sun finally reach this interstellar plasma, what do they do to it? And what does Voyager actually see when a storm that started near Earth years ago slams into the galaxy's gas at more than 100 astronomical units away? When the sun erupts, do you think the story ends once the storm blows past Earth, or do you accept that the same blast keeps going, all the way until it crashes into the galaxy itself? A big solar eruption, a coronal mass ejection, is not just a flare on the surface. It's a huge bubble of plasma and magnetic field thrown into space. Near Earth, you see the result as a geomagnetic storm. Auroras, satellite glitches, radio blackouts, current surges, and power grids. But the CME doesn't stop at one astronomical unit. It keeps going. It keeps moving outward at hundreds of kilometers per second, often 500, 800, sometimes more than 1,000 kilometers per second when it leaves the sun. By the time it reaches the outer planets, it has spread out and slowed, but it is still a coherent disturbance in the solar wind, a moving shock wave with enhanced density, magnetic field, and pressure. It keeps plowing through the heliosphere, crossing the orbits of Jupiter, Saturn, Uranus, Neptune, then running into the slowed solar wind in the heliosheath. This is already a volume much larger than the orbits of all the planets, and the same eruption that lit up Earth's skies is still out there, decades in terms of travel time, reshaping the outer boundary of the sun's bubble. Voyager is far beyond the planets now, so the natural question is, does it still feel storms that started when we were just talking about space weather near Earth, or does the influence of those eruptions fade away before they reach the heliopause? Years after it left the heliosphere, Voyager 1 still hears these old shocks, not with a camera or a particle counter alone, but with the plasma wave instrument. When a solar-driven shock finally reaches the interstellar plasma around the spacecraft, it compresses the local gas, raises the density, and kicks the electrons into collective oscillations. The instrument picks that up as a sudden burst of radio noise at specific frequencies, a sharp rising whistle or tone depending on how you play it back. Each event starts with a solar eruption near the sun, which you can see with coronagraphs and near-Earth satellites. Then you track the shock as it moves through the inner heliosphere with in-situ spacecraft. And finally, years later, Voyager detects the same disturbance as it reaches more than 100 astronomical units, out in the very local interstellar medium. That's the pattern. A blast launched close to the sun, then a long, slow journey outward, then a final impact where it rings the interstellar plasma like a bell, giving you another density measurement and another proof that the sun's influence reaches deep into galactic space. This isn't happening once, it's a repeating process. Major solar cycles produce many strong CMEs. Some of them line up with Voyager's direction, some of them don't. But whenever one does, and it is strong enough, you get a delayed echo in the data. The plasma wave bursts tell you that storm you saw at Earth is now slamming into interstellar gas out here, far beyond the heliopause. This is why those interstellar confirmation events matter so much. A solar blast travels outward, hits the plasma near Voyager, shakes it, the electrons ring, the instrument hears a specific pitch, and from that pitch you can say, out here, this far from the sun, the number of electrons per cubic centimeter is in the interstellar range. It's a very indirect method, but it's one of the only ways to get density in a place where you might have just a few tens of thousands of particles in a cubic meter. Once you can measure density like this, the next question is, how big is the jump when you leave the heliosphere? How different is the outside from the inside? Inside the outer heliosphere, just before the heliopause, the plasma density is around a couple of thousandths of an electron per cubic centimeter, about 0.002. That is already a ridiculously good vacuum, better than most ultra-high vacuum systems on Earth. Then you step outside, and Voyager's plasma wave measurements show values around 0.08 per cubic centimeter. Sometimes a bit lower, sometimes a bit higher. That is an increase by a factor of around 40 to 50. You are still dealing with an extreme vacuum. There are far fewer particles out there than in air, or even in the best lab vacuum you can build. But for the physics that control shocks, waves, and how particles are accelerated, that density jump is huge. A higher density plasma carries more current, reacts differently to magnetic disturbances, and lets different kinds of waves propagate. So the interstellar medium just outside the heliosphere is not just a bit thicker, it is a fundamentally different regime with its own characteristic behavior. That big jump is one of the reasons we say the heliopause is a real physical boundary, not just a vague region. You go from a very dilute solar wind to a significantly denser galactic plasma over a relatively thin layer. And once you're outside, you are no longer in a space controlled by the sun's outflow. You're in material that belongs to the galaxy. Density is only half the story, though. The other half is temperature, and this is where the numbers sound misleading if you try to map them directly to everyday experience. How do you process the idea that the gas around Voyager is both cold and thin, and also tens of thousands of degrees at the same time? Voyager 2, unlike Voyager 1, still has a working plasma instrument that can measure particle speeds more directly. From those speeds, you can infer a temperature. The velocities indicate that the interstellar plasma just outside the heliopause sits in a range of roughly 30,000 to 50,000 Kelvin. That is tens of thousands of degrees above absolute zero. On paper, that sounds incredibly hot, hotter than many surfaces on Earth. But this is not a temperature you would feel the way you feel air temperature on your skin. Temperature in a gas is about the average kinetic energy, the average speed of the particles. In the interstellar medium, each particle has a lot of energy, but there are very few particles per cubic meter. So the energy per particle is high, but the energy per volume is tiny. If you put a solid object there, very few particles would hit it each second, so it would not warm up quickly. You'd be in a medium where each individual proton is red hot in energy terms, but the overall environment is so empty that it cannot transfer heat efficiently. This is why calling that plasma hot can be confusing. In physics terms, yes, the temperature is high. In human terms, your spacecraft is not being baked. It is being tapped occasionally by fast particles in an almost empty volume. It's a regime that barely maps to everyday experience, because you never deal with both such low density and such high particle energies on Earth without specialized equipment. Once Voyager is outside, measuring both density and effective temperature, you can start asking a larger scale question. Does the environment out there stay constant, or does it keep changing as you move farther from the sun? Is the very local interstellar medium smooth, or does it have structure on the scale of tens of astronomical units? Analyses of several years of plasma wave data from Voyager 1 show that the electron density does not stay flat once you cross the heliopause. Instead, as the spacecraft moves another several tens of astronomical units outward, the inferred density gradually increases, not in a sharp jump this time, but in a slow upward trend. You can see the shift in the frequencies of those plasma tones. They creep higher over time, which means more electrons per cubic centimeter, even though you're far beyond the sun's main influence. That gradual rise hints at larger scale structure in the very local interstellar medium. You are not traveling through a perfectly uniform gas. You are moving through regions with slightly different densities, maybe shaped by past supernova shocks, local magnetic field patterns, or flows of gas relative to the sun's motion. It suggests that the environment our heliosphere is plowing through is made of subtle filaments, waves, and patches of varying density rather than one smooth background. For models of the heliosphere, that matters. If the external density is not constant, then the pressure on the heliopause is not constant either. Regions of higher density can squeeze the bubble more. Regions of lower density can let it expand slightly. Over long timescales, that could change the size and shape of the heliosphere in ways we are only beginning to quantify. And it means the sun is moving through a textured medium, not an ideal gas. All of that sets up an even more dynamic picture. You have a boundary where density jumps sharply, you have a background plasma outside that slowly varies, and you have a sun that keeps throwing out shocks and eruptions. The obvious next question is, when those old explosions from the sun finally reach this interstellar plasma, what do they do to it? And what does Voyager actually see when a storm that started near Earth years ago slams into the galaxy's gas at more than 100 astronomical units? When the sun erupts, do you think the story ends once the storm blows past Earth, or do you accept that the same blast keeps going, all the way out until it crashes into the galaxy itself? A big solar eruption, a coronal mass ejection, isn't just a flare on the surface. It's a huge bubble of plasma and magnetic field thrown into space. Near Earth, you see the result as a geomagnetic storm. Auroras, satellite glitches, radio blackouts, current surges in power grids. But the CME doesn't stop at one astronomical unit. It keeps going. It keeps moving outward at hundreds of kilometers per second, often 500, 800, sometimes more than 1,000 kilometers when it leaves the sun. By the time it reaches the outer planets, it has spread out and slowed, but it is still a coherent disturbance in the solar wind, a moving shock wave with enhanced density, magnetic field, and pressure. It keeps plowing through the heliosphere, crossing the orbits of Jupiter, Saturn, Uranus, Neptune, then running into the slowed solar wind in the heliosheath. This is already a volume much larger than the orbits of all the planets, and the same eruption that lit up Earth's skies is still out there, decades in terms of travel time, reshaping the outer boundary of the sun's bubble. Voyager is far beyond the planets now, so the natural question is, does it still feel storms that started when we were just talking about space weather near Earth? Or does the influence of those eruptions fade away before they reach the heliopause? Years after it left the heliosphere, Voyager 1 still hears these old shocks, not with a camera or a particle counter alone, but with the plasma wave instrument. When a solar-driven shock finally reaches the interstellar plasma around the spacecraft, it compresses the local gas, raises the density, and kicks the electrons into collective oscillations. The instrument picks that up as a sudden burst of radio noise at specific frequencies, a sharp rising whistle or tone, depending on how you play it back. Each event starts with a CME near the sun, which you can see with coronagraphs and near-Earth satellites. Then you track the shock as it moves through the inner heliosphere with in-situ spacecraft, and finally, years later, Voyager detects the same disturbance as it reaches more than 100 astronomical units, out in the very local interstellar medium. That's the pattern: a blast launched close to the sun, then a long, slow journey outward, then a final impact where it rings the interstellar plasma like a bell, giving you another density measurement and another proof that the sun's influence reaches deep into galactic space. This isn't happening once, it's a repeating process. Major solar cycles produce many strong CMEs. Some of them line up with Voyager's direction, some don't. But whenever one does, and it is strong enough, you get a delayed echo in the data. The plasma wave bursts tell you that storm you saw at Earth is now slamming into interstellar gas out here, far beyond the heliopause. From the timing of these events, you can do more than just say, it arrived. You can measure how fast the shocks are traveling on average. You note when the CME left the Sun, you record when its effects are seen near Earth, and then you note when Voyager picks up the interstellar signature. The time difference, combined with the known distance, gives you a propagation speed. Even at distances beyond 100 astronomical units, these shocks are still moving at hundreds of kilometers per second, slower than they were near the Sun, but still fast enough to cross the whole planetary region in months to years. In everyday terms, you are watching a storm expand across a region larger than the orbits of all the planets combined, and when it finally reaches the interstellar medium, it still has enough energy to compress the plasma, raise the density, and excite measurable waves. This is not a gentle ripple. It is a large-scale pressure pulse that keeps its identity for decades of travel time, and for distances measured in tens of billions of kilometers, tens of billions of miles. Those speed estimates matter because they tell you how much the solar wind decelerates as it moves outward, how shocks evolve as they pass through the termination shock and heliosheath, and how efficiently the Sun can inject energy at the edge of the heliosphere and beyond. They also connect the inner and outer heliosphere in a very direct way. A solar weather event we worry about for satellites and power grids today can be the same event that, years later, gives us a new measurement of density and field conditions in the VLISM. Now, if those shocks can make it all the way out and still disturb the interstellar plasma, what does that say about the heliopause itself? Is it a solid barrier, a wall that blocks everything, or is it something more flexible, more permeable? The fact that Voyager 1 hears CME-driven shocks after it has clearly crossed into interstellar plasma tells you the heliopause is not an impenetrable wall. It behaves more like a membrane. Pressure waves and disturbances from inside can couple through it into the outside medium. Some energy is reflected, some is transmitted, but the boundary does not isolate the Sun completely from the galaxy. When a strong shock from a solar eruption hits the heliopause from the inside, it compresses the boundary, changes its position, and launches a transmitted wave into the VLISM. This has two important consequences. First, the outer edge of the heliosphere is constantly being pushed and pulled, not only by the steady solar wind and the static external pressure, but by intermittent shocks from solar activity. That means the size and shape of the heliosphere breathe on timescales of years, shrinking and expanding, changing slightly with each big storm. Second, the Sun is not just being sculpted by the galaxy, it is also pushing back, sending ripples of pressure and magnetized plasma out into interstellar space. You often hear that the galaxy pushes on our heliosphere and sets its shape, which is true, but Voyager's view of these transmitted shocks adds the other side of the story. Our star is injecting energy into the local interstellar medium, sending waves that heat and stir the gas just outside. So there is a two-way interaction happening at the heliopause. The external medium shapes the Sun's bubble, and the Sun's eruptions send disturbances back into that medium. That raises a new question. If shocks and pressure waves can cross this boundary, what about neutral atoms, the particles that don't care about magnetic fields at all? Do they build up around the heliosphere? Do they form any kind of structure you can detect? And if so, how does that hidden layer change the flow of material into and out of our bubble? How do you build a wall out of atoms you can't really see, and then prove it's wrapped around your entire solar system? Long before Voyager ever got near the edge, models said something simple. You're moving through interstellar gas, and a lot of that gas is neutral hydrogen, not charged, not tied to magnetic fields, just atoms drifting in from the galaxy. As the solar wind runs into that gas and slows down near the heliopause, those neutral atoms don't feel the magnetic barrier the same way charged particles do. They can drift in closer, get slowed, compressed, and pile up. That pile-up region is what people started calling the hydrogen wall. The idea was, Just outside where the solar wind stalls, you should get a zone where neutral hydrogen density is higher than in the undisturbed interstellar medium. Not by a little, by enough to show up in the specific ultraviolet light that hydrogen emits. That line is called Lyman alpha. So the prediction was clear. If your models are right, you should see an excess of Lyman alpha glow from that region around the heliosphere, a fuzzy shell of extra hydrogen stacked up against the sun's outflow. Neutral hydrogen is tricky though. It doesn't respond to magnetic fields. It doesn't follow the same rules as charged plasma, so you can't just treat it as a minor correction. It punches through the magnetic structures, gets ionized inside, then turns into charged particles called pickup ions, which then join the dance of the solar wind. All of that feeds back into the pressure balance at the boundary. So before Voyager crossed the heliopause, how did you even know this wall was more than just a neat theory on paper? Voyager had ultraviolet instruments on board, designed to look at the sky in wavelengths your eyes can't see. When you use those instruments to study the diffuse ultraviolet background, you can pick up Lyman alpha light scattered by hydrogen atoms, both inside and outside the heliosphere. What the data showed was there was more Lyman alpha glow in certain directions than you'd expect from just a regular interstellar hydrogen density. That excess lined up well with the idea of a compressed region near the heliopause, a thicker band of neutral hydrogen wrapped around the sun's bubble. It wasn't just Voyager doing this. Other missions and telescopes saw similar hints. You put those pieces together and you get a picture where there's a region, tens of astronomical units thick, where neutral hydrogen is slightly more crowded than in the surrounding interstellar medium. Not a solid shell, but a swollen zone of compressed atoms, shaped by the slowdown of the solar wind and by the balance of pressures at the edge. Then missions like IBEX and Cassini added more detail. They didn't fly out there, but they used energetic neutral atom imaging, ENA imaging, to indirectly map the boundary. Charged particles at the edge of the heliosphere can steal electrons from neutral atoms and turn into neutral particles themselves. Those neutrals then fly in straight lines, back toward the inner system where detectors can catch them. From those detections, you can reconstruct where the interactions are strongest, and you see signatures that match a compressed, structured region around the heliosphere. The hydrogen wall is part of that whole picture. So if other missions are doing the pictures, why does Voyager still matter here? Why aren't those newer instruments enough on their own? Because you still need ground truth. You still need something sitting in the plasma, at the actual boundaries, measuring densities, pressures, and magnetic fields directly. IBEX and Cassini can tell you there is a structured boundary. They can tell you there are regions of enhanced interaction, but they rely on models to turn those neutral atom counts into specific densities and distances. Voyager is the one that actually flew through the termination shock, through the heliosheath and across the heliopause, and measured where the solar wind really slows down, how the density jumps, what the magnetic field strength is on each side. That lets you nail down the exact location of the compression regions and put hard numbers on how much the solar wind is decelerated before it hands over control to the interstellar medium. When you combine Voyager's in situ data with the remote sensing from IBEX and Cassini, you can anchor the hydrogen wall in real space, not just on a plot. You can say, here's where the solar wind goes subsonic, here's where it nearly stalls, here is where neutral hydrogen is expected to pile up, here is where the plasma density and magnetic field jump. And that combined picture tells you not just that there's a wall, but how thick it is, how strong it is, and how it shifts with solar activity. That might sound like a niche detail, but the hydrogen wall does more than just quietly sit at the edge. It directly affects how material from the galaxy flows into your heliosphere. Neutral atoms from the interstellar medium are constantly drifting in toward the sun. Some get ionized by solar ultraviolet light, or by charge exchange with solar wind ions. When that happens, those new ions get grabbed by the sun's magnetic field and swept into the solar wind. They become pickup ions, a population of particles that start out cold and slow relative to the solar wind, then get accelerated. Some of those pickup ions get energized further and become what we call anomalous cosmic rays, particles with higher energies than the background solar wind, but lower than typical galactic cosmic rays. The hydrogen wall region, by changing the density and flow of neutral atoms near the boundary, changes how many neutrals actually penetrate into the heliosphere, where they get ionized, and how many become pickup ions and anomalous cosmic rays. That in turn shapes the particle populations you measure all the way back at 1 astronomical unit near Earth. So even though this wall sits far out near the heliopause, its properties feed directly into the radiation environment in the inner system. Dust is affected too. The same region of compression and changing flow patterns influences how interstellar dust grains are deflected or allowed in, how they charge up, and where they get filtered out. That changes the distribution of tiny solid particles throughout the heliosphere, which matters for things like micrometeoroid impacts on spacecraft and the long-term evolution of dust populations in the inner system. So the hydrogen wall is not just a curiosity, it is another filter layer at the edge of your bubble, changing what gets in and what stays out. And because it is made of neutral atoms that don't care about magnetic fields, it interacts with the heliosphere in a way that plasma alone cannot, adding another degree of complexity to an already messy boundary. And that brings you straight to the next problem. If you have a squashed, magnetically pinched heliosphere with compressed plasma, a stronger than expected external field, and the hydrogen wall wrapped around it, what does the overall shape of this bubble really look like? Is it the neat comet tail you saw in old textbooks? And are you sure that picture survives contact with what the probes actually measured? When you picture the sun's bubble in space, do you still see that long, clean comet tail stretching away into the darkness? And are you sure that picture survives contact with what the probes actually measured? For years, textbook art showed the heliosphere as a teardrop, blunt on the side facing into the interstellar flow, then trailing a long, thin tail downstream. The logic was simple. The sun is moving through the local interstellar medium, so it should behave like an object moving through a fluid. You get a compressed nose where you hit the gas head-on, and a stretched tail where the flow wraps around and closes behind you. If you've seen a comet or a boat week, the mental image feels comfortable. You just scaled it up to solar system size and called it a day. The problem is that picture was built on analogy more than data. We didn't have in situ measurements at the relevant distances. The outer heliosphere was basically an artist's concept with a few constraints from theory. Once the Voyager started hitting real boundaries, that comfort went away. You already saw the first hint of trouble in the termination shock distances. Voyager 1 crossed the termination shock at 94 astronomical units, while Voyager 2 hit it closer in, at around 84 astronomical units. That's not a small mismatch. 10 astronomical units is over 1.5 billion kilometers, about a billion miles. The heliopause distances don't match perfectly either, around 121 AU for Voyager 1 and about 119 AU for Voyager 2, in a different direction and at a different latitude. If the heliosphere really had a simple, symmetric teardrop shape, you'd expect those crossings to be much more similar. Add in what energetic neutral atom maps from missions like IBEX and Cassini showed. Those ENA maps suggested that the regions of strongest interaction at the boundary are not arranged in a simple, long downwind extension. You see lobes, asymmetries, and patterns that don't line up with a single smooth downwind extension. Put all that together and the old comet picture starts to crack. The bubble was clearly squashed on some sides, distorted by a local magnetic field, and probably more complex on the downwind side than a clean, stretched tube of solar wind. So if it's not a neat teardrop, what does the outer shape look like when you actually run the physics with real numbers from Voyager plugged in? Recent magnetohydrodynamic simulations, MHD simulations, take the measured external density, the stronger than expected interstellar magnetic field, and the odd field orientations near the heliopause, then evolve the system. What falls out of those models is not a simple tail, but something more like a multi-lobed bubble. One popular description is croissant-shaped. You have two large lobes extending roughly above and below the solar equator in the downwind direction, with a more compact, turbulent region between and around them. In that picture, the interstellar magnetic field wraps around the heliosphere and channels the flow. The solar wind that would have formed a single long tail instead gets squeezed and divided, forming two main outflow directions. The downwind region is not a stable, narrow tube. It's a stubby, disturbed zone with turbulence, reconnection, and complex flows. You still have a nose region upwind where the heliosphere pushes into the interstellar medium, but downstream it's more like a twisted, pinched bubble than a classic comet tail. Voyager doesn't map all of this directly. Two spacecraft following two trajectories cannot give you a full three-dimensional image, but they do act as anchor points. Any model of the heliosphere's global shape has to match the distances where Voyager 1 and Voyager 2 saw the termination shock and heliopause. It has to match the plasma densities and magnetic field strengths just inside and outside those boundaries. And it has to reproduce the kinds of turbulence and stagnation regions seen in the heliosheath. That's why the croissant-style solutions are not just speculative art. They are tuned to hit those Voyager constraints, plus the ENA maps and the hydrogen wall observations. If a simulation can't get Voyager's crossing distances and field values right, it's basically disqualified. Once you enforce those numbers, you stop getting a long, narrow tail as the default solution. You get these pinched, lobed structures instead. So why should you care what exact shape this huge, mostly empty bubble takes? Isn't it just cosmetic? Just a detail for space nerds and diagram artists? The shape directly controls how cosmic rays enter the heliosphere. In regions where the boundary is thinner or more directly connected to the interstellar magnetic field, high-energy particles can leak in more easily. If you have two lobes instead of one long tail, the weak spots where radiation access is easier may be in very different places than older comet tail models assumed. That matters for understanding the cosmic ray environment at different longitudes and latitudes inside the heliosphere. It also changes where solar material escapes. The solar wind doesn't just vanish at the heliopause. Some of its energy and particles bleed out along certain directions. If the downwind side is stubby and turbulent, material may vent differently into the galaxy over time. For future interstellar probes, the global shape is not a trivia question. It's a navigation and survival problem. If you want to send a fast craft out of the heliosphere, you might want to choose a direction where the crossing is cleaner, where the boundary is thinner, or where the cosmic ray gradient is less brutal. Or maybe you want to stay inside a more sheltered lobe for longer before punching out. Depending on the mission's priorities and shielding limits, the croissant-shaped heliosphere suggests that not all exit paths are equal. Even for missions that stay inside, the shape influences how solar storms and global disturbances propagate through the outer regions, where shocks pile up, where stagnation zones form, and where density gradients are steepest. All of that feeds into the models you use to predict conditions for spacecraft operating in the outer system. So when Voyager forces you to redraw the heliosphere from a smooth comet tail into a distorted, magnetically pinched, possibly two-lobed bubble, it's not just about fixing a picture in a textbook. It's about updating your understanding of how radiation, plasma, and magnetic fields move through the space that all your planets and future missions live in. But knowing the shape of the bubble is only part of the story. The next question is, what is actually drifting through that space? How much dust? How many tiny grains are floating between the stars? And what do those almost invisible particles do to a spacecraft that's been flying at tens of kilometers per second for decades? When you think about interstellar space, do you picture perfect emptiness? Or do you accept that even almost empty can still sandblast a spacecraft over decades? Voyager carries dust detectors and plenty of engineering hardware that can double as impact monitors. When a tiny grain, maybe a few micrometers across, slams into the spacecraft at tens of kilometers per second, it doesn't bounce, it vaporizes. The grain and a bit of the surface both flash into plasma. That sudden event leaves a tiny pit and a brief electrical spike that instruments can pick up. Each hit is microscopic, but at those speeds, it's like a sand grain hitting metal fast enough to chip atoms off. Over years, and now decades, those little collisions add up. They slowly erode surfaces. They can roughen thermal blankets, pit exposed metal, and in extreme cases, a bigger grain could punch hard enough to damage a cable or a sensor. Voyager hasn't been ripped open, but the fact that it still records occasional impacts means the road out of the solar system is not clean. You are not gliding through nothing. You are plowing through a very thin, very sparse, but very real stream of solid particles. So the next question is simple. Once you get past the outer planets, does the dust finally disappear, or does it follow you into interstellar space? Measurements from Voyager and other missions show that the density of dust does drop as you move beyond the orbits of the giant planets. The thickest, most crowded regions of dust are in the inner system and around the big planets, but as you head outward, that density does not fall to zero. Even in the very local VILSM, the spacecraft still registers impacts from interstellar grains. The rate is low, but not zero. That tells you something important about the VILSM. It is not just gas and plasma. It is also seeded with solid particles, tiny grains drifting between the stars, on average separated by huge distances, but still present. If you put a sensitive detector on a spacecraft moving fast enough and leave it running for years, you will hit some of them. That means any realistic picture of interstellar space has to include a dust component, not just an idealized gas. Once you know the grains are there, the next thing you want to know is, what are they made of? Are they just simple rock fragments or something more interesting? Voyager's instruments can't scoop and analyze a dust grain directly, but impacts create characteristic signals: the size of the spike, the shape of the pulse, how it compares to similar events closer to the sun. All of that gives you clues. By comparing these signatures with what we know from meteoroids and dust in the inner solar system, scientists can infer that at least some of the grains out there carry heavy elements and more complex compounds, not just pure ice or pure rock, but material that has been processed in earlier generations of stars. That means the dust Voyager is running into in the VILSM is likely part of the general interstellar dust population. Grains that condensed in stellar winds, in supernova ejecta, and in dense molecular clouds. Many of them have been through cycles of heating, cooling, and chemical processing. You are literally flying through star ash, the raw material that can, under the right conditions, collapse into new clouds, new disks, and eventually new planetary systems, including rocky planets with surfaces, atmospheres, and maybe life. On human scales, each grain is nothing, but on galactic scales, this mixture of gas and dust is the feedstock for everything. If you want to understand how common Earth-like worlds might be, you have to understand how metals and complex molecules are distributed in the interstellar medium. The fact that Voyager still hits dust grains out past the heliopause gives you direct proof that solids, not just gas, are part of that environment. Now turn this around. Instead of asking what's out there, ask what does this do to a spacecraft that isn't crawling along like Voyager, but sprinting at truly interstellar speeds. Voyager moves at about 17 kilometers per second, roughly 61,000 kilometers per hour, about 38,000 miles per hour. Fast enough that even tiny dust grains have impact energies you have to respect, but still slow compared to the speeds people imagine for serious interstellar missions. Many Starship concepts talk about 100 kilometers per second or more. That's almost 6 times Voyager speed. At that point, the kinetic energy of an impact goes up with the square of the speed. So a grain that's annoying at 17 kilometers per second becomes potentially destructive at 100 kilometers per second and catastrophic at higher velocities. Even with the relatively low dust densities Voyager is measuring, those impact rates multiplied by the much higher energies imply serious shielding requirements. You're not just worrying about radiation anymore, you're worrying about micro bullets, each a few microns across, hitting with enough energy to drill into armor, generate shock waves in the structure, and spray fragments into delicate electronics behind the surface. It forces you to think about thick Whipple shields, sacrificial layers, angled deflectors, and perhaps smart ways to clear a path ahead of the vehicle. Voyager's long survival, moving through this environment for decades, is partly the result of conservative engineering, sturdy construction, redundancy, and partly simple luck. The spacecraft is small, the cross-sectional area is limited, and the trajectories so far have not plowed through any unusually dense dust streams. But when you design future interstellar probes, you don't get to assume you'll be lucky. You need real numbers to feed into risk calculations. How many impacts per square meter per year? At what grain sizes? At what relative speeds? Right now, Voyager's dust and impact data are basically the only in-situ measurements you have for these conditions beyond the outer planets and into the VILISM. They set the baseline for how gritty the path to the stars is. They don't cover every direction or every possible environment, but they give you a hard lower bound. Space between the stars is not perfectly clean, and any ship that crosses it at extreme speed will have to pay the price in armor, mass, and careful design. So you've got dust grains chipping away at the hull, plasma densities rising outside the bubble, shocks from old solar storms slamming into interstellar gas, and a magnetic field that is stronger and stranger than you expected. At this point, the obvious question is, if space out there is really that active, can you actually hear it? Can you turn those electric disturbances into something you can listen to, and use that sound to prove, once and for all, that Voyager is riding the edge of the solar system? How do you know what space sounds like when there's no air, no normal sound, but still plenty of things shaking and ringing out there at the edge? Voyager carries something called the plasma wave system, and its entire job is to listen, not for music, not for voices, but for tiny electric field oscillations in the audio range, the same range your ears are sensitive to. In a plasma, electrons can slosh back and forth together. Those motions generate electric waves at specific frequencies. The instrument picks up those waves and turns them into voltages that can be played back as sound. So when a shock passes, or when Voyager enters a region of different density, the plasma sings and the spacecraft hears it. Inside the heliosheath, that transition region after the termination shock, but before the heliopause, you already see bursts of these waves. Every time a coronal mass ejection-driven shock comes through, the local plasma gets compressed, electrons ring, and the instrument logs bursts at particular frequencies. Each strong event is a spike, a burst of noise, and from the frequency of that noise, you can calculate how many electrons there are per cubic centimeter. You get density from sound even though there's no air, just charged particles. Once Voyager 1 moved beyond the heliopause, those same kinds of events became your main tool for reading the interstellar plasma. You don't have a working direct plasma detector on that spacecraft anymore, so the only way to get density is to wait for some disturbance, a shock arriving from the sun that shakes the local electrons and makes them ring at their natural frequency. The plasma wave system picks it up. You see a bright line on the spectrogram, and from that line you get a number. It's a very alien way to do sensing, but it works. In April 2013, several months after the date when the particle and field data already suggested Voyager 1 had crossed a heliopause, the plasma wave system recorded a strong, sustained tone at about 2.6 kilohertz. Not a brief burst, but a tone that lasted long enough to analyze clearly. The team translated that frequency into an electron density, using the well-known relation between plasma oscillation rate and density, and it came out to roughly 0.08 electrons per cubic centimeter, right in the expected range for the very local interstellar medium, far above the 0.002 or so you see in the outer heliosphere. That single event became a key piece of evidence because it matched what theory said interstellar plasma should look like near our region of the galaxy, and it did not match what you'd expect from any plausible extension of the solar wind. If Voyager had still been in an odd extended heliosheath, the density would not have jumped to that value. The 2.6 kilohertz tone was basically the universe's tuning fork being struck, giving you one clear note that encodes the density of the medium around the spacecraft. More such events followed as other shocks from big solar eruptions finally reached Voyager's position. Each one set the local plasma ringing at similar, slightly varying frequencies, and each time the inferred density stayed in that interstellar range. The pattern was consistent. This isn't just a one-time glitch. It's a series of confirmations that the environment out there is denser than the outer solar wind, and firmly in the VILISM region. When you string years of this data together, another picture shows up. It's not just isolated notes, it's a kind of background chorus. The analyses found that plasma waves in the interstellar medium around Voyager are not rare. You see long-lasting structures, slowly changing frequencies, and a general trend that the characteristic frequency, and therefore the electron density, climbs as Voyager moves further out. Over something like 30 astronomical units of travel, the inferred density gradually rises, which is how we know the interstellar plasma isn't uniform. It has gradients and large-scale structure. On top of that trend, you see turbulence. The spectrum of wave contains more than just a single pure tone. There are broader bands, signatures of random motions, interactions with cosmic rays, and the influence of large-scale magnetic structures. Shocks from the sun add extra spikes, but even between them, the plasma is not quiet. It is constantly being stirred by the combination of galactic processes and the lingering influence of the heliosphere. So when we talk about the heliopause as a busy borderland, this is what we mean. It's not a silent line, it's a region that hums with measurable, quantifiable activity. And that leads to a bigger scale question. If the sun's influence can still be heard out there in these delayed echoes, what happens when you step back and look at slower, longer changes, like the sun's 11-year cycle? Can Voyager, sitting more than 120 astronomical units away, still feel that heartbeat? And if it can, what does that say about how far the solar cycle really reaches into interstellar space? If the heliopause is really the border, once Voyager is outside, does the sun still matter, or does it just fade into the background and let the galaxy take over completely? The sun runs on an approximately 11-year cycle. You see it in the number of sunspots, the rate of flares, and the strength and complexity of the solar magnetic field. At solar maximum, the field is tangled and strong. Eruptions are frequent, the solar wind is more disturbed. At minimum, the field is simpler and weaker. The wind is calmer. Near Earth, you can see that cycle clearly in space weather data, but Voyager is over 120 astronomical units away, well into interstellar plasma, so the key test is, does that 11-year pulse still show up that far out? The answer is yes. Even from that distance, Voyager sees the cycle, not as sunspot counts, but as slow changes in cosmic ray intensities, magnetic field behavior, and the rate and strength of shock arrivals. During parts of the cycle when the sun is more active, the heliosphere is pumped up, shocks are more common and stronger, the boundary is more compressed, and the modulation of cosmic rays is stronger. So even in interstellar space, the instruments record that the environment is different in those periods. You're so far away that by the time a specific solar storm gets there, it's old news on Earth. Years have passed, but the signature still shows up in the data as a delayed echo of that cycle. This is where the idea of the heliosphere as a variable shield becomes very concrete. The solar wind and the magnetic field it carries don't just block cosmic rays in a static way. They change their effectiveness over the cycle. At solar maximum, stronger, more turbulent fields make it harder for some cosmic rays to penetrate. The overall intensity inside the heliosphere drops. At solar minimum, when the field is weaker and less tangled, more galactic cosmic rays can get in. The shield relaxes. You can see that clearly at Earth in long-term neutron monitor data and in spacecraft detectors. What Voyager adds is the view from the edge. Its instruments see how this modulation behaves not just at one astronomical unit, but all the way out at the heliopause and beyond. The changes in cosmic ray intensities out there are smaller in relative terms than near Earth, but they are still there. The flux of high-energy particles rises and falls in step with the solar cycle, just with a delay and with some smoothing from the long travel distance. Those measurements are critical for realistic models of cosmic ray transport because they tell you how the shield behaves over the entire bubble, not just at one point inside it. If you want to build a proper model, you need boundary conditions. You need to know what the cosmic ray intensity is right outside the heliosphere, how it is modulated at the edge, and how that modulation propagates inward. Voyager is giving you the outer boundary, ground truth for the incoming flux and its time variation. From there, you can simulate how the spectrum of particles evolves as it moves toward the inner system, and compare that with what satellites near Earth see. That's how you know your transport physics is actually right. The time delay aspect is also very useful. When a large coronal mass ejection erupts from the sun, it reaches Earth in a few days. You get your auroras, your geomagnetic storm, your satellite warnings, then everyone forgets and moves on. But that same event, if it's directed roughly along Voyager's line, takes years to reach the outer heliosphere, and then the interstellar medium. By the time it does, it has slowed down and spread, but it's still a coherent pressure pulse. Voyager sees the resulting shock and plasma wave signatures as a late hit. So you end up with something like a two-stage weather report. You log the event in the inner system when it happens, and then years later, you see the echo at the edge. By comparing the times, you can work out how fast the disturbance was traveling at different distances, how much it decelerated, how much it broadened, and how much energy it dumped into the heliosheath and the VLISM. In other words, you can watch the life cycle of a solar storm across a volume bigger than the orbits of all the planets combined. That is not just a curiosity. It feeds back into your understanding of how the heliosphere interacts with the galaxy. If shocks remain strong out to the heliopause and beyond, they contribute to heating and stirring the interstellar plasma. They modify local densities, and they may even play a role in accelerating certain particle populations near the boundary. Voyager's delayed view lets you quantify that instead of just speculating. Over decades, as Voyager keeps sampling, you also get something slower and more subtle, a record of whether the heliosphere itself is changing size and strength as the sun ages and as its long-term output evolves. The 11-year cycle is the short-term rhythm, but on top of that, there can be trends. Maybe the average solar wind pressure changes. Maybe the average interstellar conditions drift. Those would show up as shifts in where the heliopause sits, in how strong the shielding is on average, and in the baseline cosmic ray levels inside. For planets and moons in the outer system, and for any future habitats or long-duration missions out there, this is not an abstract detail. If the heliosphere shrinks, more galactic radiation gets in. The baseline dose rates rise, electronics fail faster, humans need more shielding. If it expands, conditions get slightly less harsh. Over geological timescales, these changes may even affect atmospheric chemistry and climate for worlds with thin magnetic protection. And when you extend this logic to exoplanets, it becomes even more important. You can't talk seriously about habitability without accounting for how a star's wind and field carve out an astrosphere and how that astrosphere evolves. So by watching the solar cycle from more than 120 astronomical units away, Voyager is doing more than just confirming that the sun's influence reaches far into interstellar space. It is giving you a time series of how that influence changes, how the shield pulses, and how that pulse shapes the radiation environment throughout the bubble, including the space around Earth. All of that sets up a final, very direct question. When you say, we've left the solar system, what do you actually mean now? Is it about distance, about gravity, about plasma, or about radiation? And where exactly does Voyager's data force you to draw that line? When you hear someone say, we left the solar system, what do you think that sentence actually means? What line do you think we crossed? You've been given a few different pictures over the years. One is simple. Once you're past Pluto, you're out. That's the edge. Another says, no, you need to clear the Kuiper belt, that ring of icy bodies beyond Neptune. A third moves the line much farther, out to the distant Oort cloud, a huge shell of comets that probably extends tens of thousands of astronomical units from the sun. And then there's the version space physicists use, which ties the border to the heliopause, the place where the solar wind loses control and the interstellar medium takes over. Each of those definitions is based on a different piece of physics. You can define the solar system gravitationally. You're in as long as you're bound to the sun's gravity. By that measure, Voyager has absolutely not left. It's still in a long, slow orbit controlled by the sun, and it will be for a very long time. You can define it in terms of material. You're inside as long as you haven't cleared the main reservoir of comets in the Oort cloud. By that standard, we're nowhere close. We're not even at a few percent of that distance. Or you can define it dynamically, which is what space physics does. You look at who owns the local plasma and magnetic field, the sun or the galaxy. Inside the heliosphere, the solar wind dominates. The plasma and fields are solar. Outside, the very local interstellar medium dominates. The plasma and fields are galactic. So from that point of view, the critical border is not Pluto, not the Kuiper belt, and not even the Oort cloud. It's the heliopause. Voyager's data make that dynamic definition concrete. When Voyager 1 crossed the heliopause at about 121 astronomical units and Voyager 2 at about 119, the character of the environment changed. The plasma density jumped to interstellar values, the spectrum of cosmic rays shifted to the galactic pattern, and the magnetic field strength matched what you'd expect from the compressed external field. By those metrics, they went from being inside the sun's plasma bubble to being outside it. So when space physicists say Voyager is in interstellar space, they're using that operational definition. They're saying the plasma and fields we measure now belong to the galaxy, not to the solar wind. That's a clean scientific criterion, even though gravitationally the probes are still very much tied to the sun, and even though they are nowhere near the outer edge of the Oort cloud, which might sit at 50,000 astronomical units or more. This is why you sometimes hear two apparently conflicting statements. Voyager has reached interstellar space, and Voyager has not left the solar system. They're both true, they're just using different definitions. One is about who controls the plasma. The other is about whose gravity still rules and where the last bound comets live. If you don't specify which rule you're using, the language gets messy fast. Even with the dynamic definition, the border is not a clean mathematical surface. Voyager's data show that the heliopause is thin, on the order of less than a tenth of an astronomical unit along Voyager 2's path, but not perfectly sharp. Densities fluctuate on both sides, the magnetic field strength and direction change in complicated ways, and shocks from the sun cross the boundary and disturb the interstellar plasma outside. On top of that, the 11-year solar cycle modulates conditions at the edge, pushing the heliopause in and out over time. That means even inside versus outside in the plasma sense is fuzzy. The boundary breathes, it moves, it wrinkles. Some regions might be more permeable to cosmic rays or neutral atoms at certain times, others less so. You can draw an average surface for the heliopause, but at any given moment, the real edge will be a bit closer in here, a bit farther out there, responding to both solar activity and changes in the local interstellar medium. Voyager caught that in real time, with shocks arriving years after they left the sun and still shaking the boundary. So what are you actually saying, in plain language, when you claim we've left the solar system now that Voyager exists? You're not saying we've escaped the sun's gravity. We haven't. You're not saying we've passed the last comet or reached the outer Oort cloud. We're nowhere near that. What you are saying in the space physics sense is this: we have crossed the region where our star's plasma and magnetic fields stop dominating local space. We are now measuring plasma, magnetic fields, and cosmic rays that belong to the galaxy first and to the sun second. The important part is, Voyager lets you attach real numbers to that statement. Densities on the order of a few hundredths of a particle per cubic centimeter, magnetic fields of a few tenths of a nanotesla, cosmic ray intensities higher than inside the heliosphere, and sharp gradients at the boundary. Before Voyager, you just had diagrams and simulations. Now you have actual data points, the first hard measurements of what interstellar space looks like right outside our bubble. And that immediately raises the next problem. If your models of the heliosphere were built before these numbers existed, how many of them survive? How many neat, smooth, idealized bubbles have to be torn up and rebuilt now that a real spacecraft has punched through the edge and sent back the actual conditions? How much of your picture of the solar system's edge survives once a real spacecraft actually flies through it? And how much turns out to be a guess that needs to be thrown away? Before Voyager got there, everything about the heliosphere's outer boundary came from models and indirect data. People had to assume values for the interstellar density, the flow speed of the gas past the sun, the strength and direction of the local magnetic field, and even how much pressure cosmic rays contributed outside. Then, they plugged those numbers into global simulations, magno-hydrodynamic codes that treat the plasma as a conducting fluid, and let the system evolve. Those pre-Voyager models did produce plausible-looking heliospheres. You got smooth, rounded shapes, either nearly spherical or with a neat comet-like tail. You got a termination shock at some reasonable distance, a heliosheath, and then a heliopause where the solar wind handed off to the interstellar medium. The density jumps at the boundary were there, but they were moderate, not extreme. The heliopause had a some thickness, and the magnetic field direction inside and outside behaved in simple, clean ways. When drawings were made from those simulations, they looked tidy and convincing. The problem is, when you don't have in situ data, you can tweak those inputs and still get something that looks about right. There's no hard anchor. So many different parameter sets can produce versions of the same smooth bubble. You might think you've nailed the physics, but really you've just built a good-looking guess. Voyager's actual measurements cut straight through that ambiguity, and they did not line up with a lot of those older expectations. One glaring discrepancy is the plasma density outside the heliopause. Many pre-Voyager models assumed values significantly lower than what the probe saw, something like a few thousandths to a couple of hundredths of a particle per cubic centimeter. When Voyager 1's plasma wave instrument and Voyager 2's plasma detector finally sampled the very local interstellar medium, they came back with densities in the range of about 0.04 to 0.08 electrons per cubic centimeter, right up at the upper end of what people thought was possible. On top of that, the heliopause itself turned out to be thinner and sharper than most simulations had built in. Along Voyager 2's path, the change from solar wind plasma to interstellar plasma happened over less than 0.1 astronomical units, under 15 million kilometers, about 9 million miles. That's razor thin compared to the overall size of the heliosphere. Older models often had broader transition regions, smoother gradients, and less abrupt changes, because no one had a strong reason to make the boundary that tight. Then there's the magnetic field direction, which was expected to flip clearly as you cross from the sun's spiral field to the galactic field outside. Many models built that flip in as a basic feature. Inside, you point roughly one way, outside, you point in a noticeably different direction. Voyager didn't see that neat behavior. The field strength outside was higher than expected, but the direction rotated modestly, staying surprisingly close to the inner heliosphere orientation. That means the actual geometry of the field near the boundary is more complicated, or the local interstellar field is more aligned with the solar field than those models assumed. Either way, the simple inside versus outside angle change doesn't show up the way it was supposed to. Once those discrepancies were on the table, the old simulations couldn't just be patched with a small tweak. They had to be rebuilt with Voyager's numbers as hard constraints. Newer MHD models now start by tuning the external plasma density to match that 0.04 to 0.08 range. They adjust the strength and angle of the local interstellar magnetic field so that when the system settles, the heliopause sits near 120 astronomical units in Voyager-like direction and produces the right field strengths on each side. Cosmic ray pressure, which used to be treated as a minor background term, is now taken more seriously because the Voyager cosmic ray data show that these particles contribute non-negligible pressure in the outer heliosphere and just outside it. That pressure can push on the boundary and change its shape, so updated models include it explicitly, rather than hiding it in a generic external pressure parameter. In other words, the simulations now have to agree with densities, fields, and particle intensities, not just with a visually nice bubble. The result is that Voyager has basically become the set of boundary conditions for any serious heliosphere model. If your code can't reproduce the termination shock distances of roughly 84 and 94 AU along the Voyager 2 and Voyager 1 paths, the heliopause crossings at about 119 and 121 AU, the external density range, and the measured field strengths and directions, then your model is wrong, no matter how pretty the plot is. Voyager turned a vague, under-constraint problem into a tightly anchored one. This matters far beyond just solving the puzzle of our own solar system's edge, because every star is doing some version of this. Every star with a wind carves out an astrosphere in the interstellar medium around it. That bubble sets the local radiation environment for any planets in that system. It modulates galactic cosmic rays, shapes which particles reach the atmospheres, and influences long-term habitability. When you look at a distant star with planets in its habitable zone, you can't fly a Voyager there, but you can take the physics you've calibrated here and apply it there. If you know the star's wind strength, its motion through the local gas, and some estimate of the surrounding medium's density and magnetic field, you can simulate its astrosphere, estimate how strong its cosmic ray shield is, and get a first-order idea of how harsh the radiation is on any Earth-like planet around it. Voyager's measurements, especially in the 0.04 to 0.08 centimeters cubed density range and the few tenths of a nanotesla field range, become the reference point. If your model of some other star's astrosphere uses similar inputs, you can trust it more because you've already tested the same physics against data here. If it needs very different conditions, you still know what a real, measured astrosphere looks like for comparison. So when Voyager breaks the old models of the heliosphere and forces a rebuild, it's not just fixing a local mistake. It's providing the calibration for interpreting space weather and radiation around other suns. That's a direct link from a 1970s probe in the outer reaches of our system to the way you think about exoplanet safety and long-term habitability light years away. And once you have that calibration, you can finally talk honestly about what future ships will face when they stop just dipping a toe into interstellar space and start plunging through it at much higher speeds, with people and fragile hardware on board, using real numbers instead of optimistic guesses. If Voyager is just a box of instruments spinning out numbers, why should any of those numbers matter for living cells on a planet or for ships you might send after it? Out in the very local interstellar medium, Voyager has now measured what raw galactic space looks like in terms of radiation, plasma, and magnetic fields. You know the density of electrons out there is around 5 to 800th per cubic centimeter. You know the magnetic field is a few tenths of a nanotesla. And you know the intensity and energy spectrum of galactic cosmic rays is higher than what you see inside the heliosphere. That is your baseline. That is what space around other stars looks like if they had no protective bubble. Now compare that to what you measure near Earth at 1 astronomical unit inside the sun's shield. Neutron monitors on the ground, satellites in orbit, and deep space probes closer in all tell you that the heliosphere cuts down and reshapes the cosmic ray spectrum. The total intensity of high-energy particles is lower, the energy distribution is different, and the way it changes over the solar cycle is tied to the sun's magnetic field. When you put the inner and outer datasets side by side, you can quantify, not just guess, how much protection the heliosphere gives you. For DNA and for atmospheres, that gap matters. High-energy cosmic rays break molecular bonds, knock atoms out of place, and create showers of secondary particles when they hit an atmosphere. Over long timescales, that influences mutation rates, cancer risk, and even atmospheric chemistry. If the heliosphere didn't exist, or if it were much weaker, the flux of those particles at Earth's orbit would be closer to what Voyager sees outside. You would be living under a harder radiation regime, and the long-term history of life on this planet might look very different. That's not speculation anymore. It's a comparison backed by measurements at both ends of the shield. The atmospheres of other planets and moons in the outer system feel this too. Many of them have weak or no global magnetic fields of their own, so the heliosphere is their primary defense against galactic radiation. If the heliospheric shield shrinks, they get hit harder. If it expands or strengthens, they get a bit more breathing room. Voyager's numbers tell you how much the background changes if that shield ever fails, or if you go beyond it altogether. Now, take that environment and apply it to engineering. If you want to design a real interstellar mission, you need numbers, not vague statements like space is dangerous. And that's exactly what Voyager has given you. Just outside the heliosphere, you're in a plasma with densities around 0.05 to 0.08 per cubic centimeter. You're in magnetic fields of roughly 0.4 to 0.5 nanotesla. And you know the intensity and energy spectrum of galactic cosmic rays is higher than what you see inside the heliosphere. That is your baseline. That is what space around other stars looks like if they had no protective bubble. For any Starship concept, fusion rocket, laser-driven sail, beam-powered ship, whatever you like on paper, these parameters control how thick your radiation shielding has to be, what materials you can use without them degrading too fast, and how many single-event upsets your electronics will see per year. Every cosmic ray hit can flip a bit, triple latch, or damage a transistor. So the difference between inside and outside the heliosphere changes your expected failure rates, and therefore your redundancy strategy and your software error correction requirements. Communication is constrained too. Voyager's current distance, tens of billions of kilometers, already pushes the limits of what big radio dishes on Earth can pick up from a tiny transmitter with just a few watts of power. Double or triple that distance, and the signal gets weaker by the square of the distance. On top of that, a higher cosmic ray background and a more turbulent plasma environment outside the heliosphere add noise and scintillation to radio paths. That affects how much power you need, how big your antennas have to be, and how much error correction you need in your link budget. Again, Voyager's real-world link performance gives you hard data on what actually works in that regime. Speed is the next problem. Right now, Voyager's roughly 17 kilometers per second is your benchmark, around 61,000 kilometers per hour or 38,000 miles per hour. Fast by human standards, slow by interstellar standards. Serious proposals for interstellar probes talk about 100 kilometers per second, 300 kilometers per second. In some concepts, 1,000 kilometers per second. That's 6 to 60 times faster than Voyager. Once you go into that range, every dust grain becomes a high-energy projectile. The kinetic energy of an impact scales with a square of velocity, so if you increase speed by a factor of 10, the impact energy goes up by a factor of 100. Even at Voyager's modest interstellar speed, the dust and plasma measurements show that the VLISM is not dust-free. It has a non-zero population of micron-scale grains. Over decades, those grains slowly erode surfaces and leave pits. If you scale that up to 100 or 1,000 kilometers per second, you are looking at an environment where a single grain, invisible to any normal camera, can release enough energy on impact to punch through multiple layers of shielding, generate shock waves in the structure, and spray fragments into your internal systems. Because you don't have a faster probe yet, Voyager's long baseline data are the only real input you have for how many grains of what size you hit per square meter per year in this region of space. You can combine that with the velocities you want and compute realistic risk curves, how thick a Whipple shield you need, how much mass you have to accept just to keep the vehicle intact over a decades-long mission, how much extra redundancy you must build in for sensors and radiators that will be slowly sandblasted. Those are not thought experiments. They are engineering constraints that come straight out of the Voyager environment measurements. If you fold in acceleration requirements, you hit another wall. To get from 0 to 100 kilometers per second in a useful time without crushing a crew, you're limited to accelerations on the order of a fraction of a g to maybe a few g for short burns. At 1g continuous acceleration, you reach 100 kilometers per second in a matter of days. But sustaining that for big, heavy ships is a huge power and propellant problem. So most realistic designs will use lower thrust for longer, which means they spend more time in the outer regions taking more radiation and more dust hits. Again, Voyager sets the baseline for what that environment actually is. All of that can sound abstract until you zoom back in on what Voyager is physically doing right now. This is not an artist's concept, it's a real object with a real position, sending real data. By the end of 2026, Voyager 1 will be roughly one light day from Earth, around 26 billion kilometers away, about 16 billion miles. Light itself, the fastest thing there is, will take about 24 hours to make a round trip. A radio signal leaves antennas on Earth, crawls out there for almost half a day, reaches an aging spacecraft running on shrinking power, triggers a response, and then the reply crawls back for almost another half day. At that distance, when you say we've touched interstellar space, you are not using poetic language. You are describing the fact that a human-built machine is sitting in galactic plasma outside the sun's wind and returning numbers, densities, magnetic field strength, cosmic ray intensities, dust hit rates. That shattered the old picture of a neat, simple edge to the solar system. Instead of a smooth, spherical shell or a long, tidy tail, you have a distorted, magnetically pinched, dynamic boundary, a breathing shield that filters radiation for everything inside. From the perspective of life, those measurements define how much protection a star can give its planets. From the perspective of ships, they define what it will actually cost to leave that protection behind, in mass, in complexity, and in risk. Voyager has turned the edge of the solar system from a drawing into a hostile, measured environment you have to design for. And that leaves one last uncomfortable tension. You now know how far away this frontier is, how harsh it is, and how slowly you are moving toward the stars. So the final question is, with current technology and current speeds, what does going to the stars really mean for you? And how do you deal with the fact that even your fastest messenger is still barely outside your own front door? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.